The applications of exponential functions are tremendous, and being able to evaluate them and graph them are good skills for finding models that fit real-world data. For example, I don't mean to sound like a money lover or whatever, but if you invest your money will grow exponentially. If there's a bacteria or a mosquito that has invaded an area, the number of bacteria or the number of mosquitoes will grow exponentially. Or if you have a new car and you drive it off the lot, the value of your new car will decay very quickly, but then towards the end of its life it will flatten out. So it will decay exponentially. So we're going to look at situations where things grow exponentially and where things decay exponentially. Carbon dating of dinosaur fossils or just bones, relics, they decay exponentially, so scientists can determine their age based on that model. So again, we're going to model and look at a drug in your blood system. So say you take an antibiotic, or say you take an antihistamine or something. We're going to look at the decay rate of that leaving your body, or even some Tylenol. Or you drink coffee. We'll look at the decay rate of the caffeine in your body. But let's look at some graphs of exponential functions and determine what they would look at. So let's just look at number 1, which is 3 to the x power. And because I know that this is going to grow exponentially, I'm going to start with some numbers for x that include some negative numbers, and I'm going to make sure I include 0, and then I'm going to include some positive numbers, and I'm going to try to do the arithmetic. So 3 to the negative 2 means 1 over 3 squared, which is 1/9. 3 to the negative 1 means 1 over 3 to the first power, which is 1/3. How about 3 to the 0 power? Oh yeah, 3 to the 0 power is 1. And then how about 3 to the first power? It gets easier when these are not negative exponents. 3 to the first is 3. 3 to the second is 9, and 3 to the third is 27, and this is the growing exponentially. Let's graph this data. So when x is a negative 2, y is 1/9. So I'm trying to just have it be above the x-axis. When x is a negative 1, y is 1/3. When x is 0, y is 1. That's a very common ordered pair as long as you just have a base raised to a power. When x is 1, y is 3, and when x is 2, y is about right here, 9. So I'm going to draw this in red. Here's the exponential growth curve where I have a 3 as my base. Also, would you please know that this will never go below the x-axis, because it doesn't matter if you put a negative 2 in for x, or if you put a negative 100 in for x. No matter what, you're going to have 1 divided by some huge number. And 1 divided by 3 times itself 100 times is almost 0, but it's not 0. So what we say over here is that when these curves are numbers greater than 1, when a is greater than 1, the graph increases from left to right. So see this right here? Increases from left to right. The greater the a value is, the steeper the curve. I'm going to show you that in a minute. So with this going from a 2 to a 3, this curve is steeper. This curve is steeper yet. The x-axis is an asymptote. The x-axis is an asymptote. It means that that red line should never go below this asymptote. You cannot cross that because you will always have 1 divided by some big number. And would you know that all of these will cross the y-axis when x is 0 at 1? because any number raised to the 0 power will always be 1. Let's take a look at our graphing calculator, and let's graph y equals 2 to the x power. And let's just go ahead and hit graph. So there's a curve that's kind of steep, but not as steep as the one we just did by hand. 3 to the x power. So here's 2 to the x is already there. Here comes 3 to the x, a little bit steeper. Would you notice that they both cross right here, and would you notice that nothing has gone down here? They can't show the pixels above the x-axis because the calculator doesn't have enough pixel strength, if you will. And then let's go down here and put in 10 to the x power, and watch how steep this one is. Very steep, very dramatic. That's because 10 to the first is 10. 10 to the second is 100. 10 to the third is 1,000. Whereas 2 to the third is only 8. So this is how you want your money to grow. I'm kind of joking, you know, not possible. But exponential growth is good in some ways. All right, let's look at when the base is not a 2, a 3, a 10. In other words, not bigger than 1. Now I'm going to look at this where the base is between 0 and a half. It will never be less than 0. So half, a third, a fifth, always a fractional exponent. So let's do this one by hand. So again, I'm going to choose to put in negative numbers and 0 because I always want to raise this to the 0 power because I always get 1 and 2 and maybe 3. So when I put a negative 2 in here for x, 1/2 to the negative 2 power, remember one of the other rules for exponents, when you have a fraction raised to a negative power, you can flip that fraction and raise it to the positive power. So 1/2 to the negative 2 is 2 squared, or 4. And 1/2 to the negative 1 is 2 over 1 to the first power, or 2. 1/2 to the 0 power is 1. 1/2 to the first power is 1/2. 1/2 to the second power is 1 over 4. 1/2 to the third power is 1 over 8. And I just keep multiplying that denominator by 2. So 1 over 16. Let's graph this. The first order pair is to the left 2 and up 4. The next order pair is to the left 1 and up 2. The next order pair, I don't go anywhere in the x direction, I go up 1. That's always right here. It says all of these cross the y-axis at 0, 1. And the next is x is 1, y is 1/2. The next is x is 2, y is 1/4. X is 3, y is 1/8. X is 4, y is 1/16. And I'm trying to show you that this is going to try to approach the x-axis. It's going to try to touch the x-axis, but I can never let it touch the x-axis. So I'm trying to be exaggerative here. I got to keep this thing above because the x-axis is an asymptote. And as this goes out to become like a 10, for example, 1/2 to the 10th power is 1 over 2 times 2 times 2 times 2 times 2, 10 times, and I'm sorry I didn't do it. It's 32 times 32, whatever, 900 and something, or 1,000. Probably 1,026. But anyway, 1 divided by 1,026 is still not 0. So get your graphing calculator out and look at these right here. These are getting smaller. We've got 1/2, then 1/3, then 1/5. Again, please look at your exponential growth curves, and we're going to go in here now and we're going to put in 1 divided by 2 to the x power, and then 1 divided by 3 to the x power, and I forgot the parenthesis. So I'll go insert a parenthesis, and then 1 divided by 5 to the x power. And let's look at the graphs of these as this gets smaller. So the first one is 1/2. And then here comes 1/3. So as that fraction gets smaller, the steepness of that exponential decay, I didn't mean to get rid of the graphing calculator, but the steepness of that exponential decay gets greater. All right, so when a is between 0 and 1, the smaller a is, the steeper the curve. The x-axis is an asymptote, so this right here you still don't cross, and all of these cross the y-axis at 0, 1. We'll come back and graph a couple more that are a little bit harder than an inverse function, and then we'll graph some applications of this.